Hi, everyone. Thank you for coming. Okay, so these are our RU students, participants, and they're going to talk to you about their research over the past 4 weeks.
So, first up, thanks everyone for coming to our presentation today. We are the first year RU, math RU of UNL. My name is Henry.
My name's Andy.
My name's Tyler.
I'm Brian.
My name is Gabby.
And this is a presentation about finding for cohomological support varieties via graph theory.
Okay, now for a little bit of algebra background. We didn't learn this, but it is important, like, for our motivations. Okay, associated to the commutative ring, there's a geometric object known as its cohomological support variety, which encodes deep information. These varieties are extremely difficult to compute exactly, and even knowing when the cohomological support variety of a ring is maximal is not an easy task.
Our main focus was about graphs. So to provide context, a graph is a combinatorial object consisting of a collection of vertices, which we represent in our graphs as dots, and a collection of edges, which we represent as lines. Joining some of them. Associated to a graph, one may form a commutative ring known as the Stanley-Reasoner ring by, loosely speaking, taking a polynomial ring with one variable for each vertex and modding out by the products of variables given by the edges.
So what is our goal? All right, so the goal of this REU was to study among a certain collection of graphs that we it's like a cohomological support variety of associated, like, Stanley Reasoner ring, where like the Stanley Reasoner ring is maximal. As it turns out, we do not need to know anything about commutative rings and their cohomological support varieties to tackle this question. We can translate the entire problem into a question about graphs.
So Briggs, Grifo, and Pollitt have a theorem that provides combinatorial criteria that implies Stanley Reasoner rings have a maximal support variety. In particular, if a graph contains a subgraph that satisfies certain properties, the conclusion follows. We have to find 3 properties based on their criteria called A, B, and C. Property C is the absence of properties A and B, and moreover, this implies the Stanley Reasoner ring has a maximal support variety.
Now, how do we exactly interpret subgraphs? First and foremost, subgraphs are fundamentally important to the host graph as we're able to find property C. And we will assume all subgraphs do not contain any isolated vertices as they don't really affect the properties. So here's an example. The host graph is this entire square, and our subgraph are these 2 shaded edges. So what's not included in a subgraph are these 2 dotted edges and this isolated vertex.
So we have our A properties here, which for A1, it means that there's a disjoint edge that can be added, which is represented by this red dotted line. And then for A2, we have that it just means that there is a disjoint edge, which is the red line that we added that we could have added from A1. So this tells us that every A1 will give rise to an A2.
Our B properties are somewhat similar. B1 means that you can add an edge into a subgraph without adding a vertex. That's represented by the red dotted line in the first example. B2 is similar. It means you can remove an edge without changing the amount of vertices. So for example, in that example, you could add in, it has a red edge. If you removed the red edge, you wouldn't change the amount of vertices in the vertex set. B1 gives rise to B2 and vice versa.
And for our final property, property C, it occurs when the graph has neither property A nor property B. So for example, in this graph, it does not contain any property A's because it does not contain a disjoint edge, and there's no way to add a disjoint edge using the subgraph. And then it also does not have any property B's because it is impossible to add or remove an edge without changing the vertex set.
So our research question. If there's a graph with property C, it implies that the Stanley-Reisner ring associated with the graph has maximal cohomological support. Since we only have 4 weeks at this internship, it would be too ambitious for us to find all the graphs that have maximal cohomological support. So we just mainly focused on paths, cycles, and graphs with 6 edges. Okay, so how do we define paths and cycles? So P of n is a path of n vertices, which the edges connect from one vertex to the next. P5, which there's an example up there, and consists of 5 vertices with 4 edges that are connected between the vertices. While C of n is a cycle and on n vertices constructed by a path with an additional edge connecting the beginning and end vertices. So let's take, for example, this vertex right here. If we were to connect it all the way around back to itself, it would have an additional edge, which would make it a cycle.
So during the bulk of our internship, we mainly look for patterns that exist within the subgraphs with property C, and to find the host graph with those subgraphs. Something we found for paths is that all the paths with odd amount of vertices will always contain a subgraph with property C. For instance, the P7 up here, below it is one of its subgraph that has property C. And as for cycles, we found that the only cycles that contain a subgraph with property C are those with 0 mod 4 vertices. In other words, the amount of vertices is divisible by 4 with 0 remainders. An example of that is the C8 right here with the subgraph with C property next to it. So how do we know these patterns actually work? So to begin, let's establish that between 2 vertices, right? There's only 2 options you have. You either connect them, we represent that with a line, or we can leave a gap. We show that with a dotted line. So we discover that for property C to exist, it must not be anything of a kind, because 1, if you have 3 consecutive edges, it always produces a B2, highlighted in the red edge right there. And 3 consecutive gaps will always produce an A1, red dotted. So beside the 3 of a kind problem above, here are the 2 ordered patterns that will prevent you from having a subgraph with property C. The first one is you have a dotted line sandwiched by 2 edges. This will always produce a B1. And the second pattern is the edge surrounded by 2 gaps. That will always produce an A2.
Okay, there are 4 cases to start a subgraph on a path or cycle. We consider these to find a subgraph with property C. So for example, the first 2 examples up there, we cannot add an edge to the first one or a gap to the second one, because then we would have 3 of the same kind in a row, which makes it so that we can't have property C in that subgraph. And for the bottom 2, we cannot add an edge to the third one or a gap to the fourth one, because then we have one in the middle sandwiched by 2, like the opposite on the ends, which also produces either a property A or B, so then we can't have property C. Okay, because of the patterns we've found, we want to avoid them, right? So given the first 2 edges, we can figure out what the following edges have to be in order for the graph to contain property C. We found the following pattern that is necessary for cycle graphs to contain or to have a subgraph with property C. This is seen on the board. It's 2 edges followed by 2 gaps. And this pattern repeats itself in cycle graphs for it to have property C.
So how do we know that this pattern works and why? This pattern works because it avoids the three of a kind that Gabby just mentioned, or any sandwiches. And if we continue this pattern, we start to get these graphs with property C. Notice how there's not three in a row and there's not a sandwich, as in there's not a shaded, gap, shaded, or vice versa. It follows the pattern as there's two shaded, two gap, two shaded, two gap. And another example would be right here, where there's two shaded and then two gap.
So we explore that patterns for paths also. We ask ourselves, does that pattern works for paths? Let's look at the smallest path with a subgraph containing C property, which is the P3 graph up there. We have another two graphs with subgraphs containing property C, or the P5 and the P7 down here with the subgraph containing property C. Notice how all these paths, they all have an odd amount of vertices. So that leads us to two cases for odd paths, right? The first case are the path containing 4n minus 1 vertices. In that case, we must start and end with the two edges. An example for a path with 4n minus 1 vertices is if you plug in 3 for n, you get P11. And the subgraph below with C property, you notice how the first two edges and last two edges are like lines. And in the other case, of path with 4n plus 1 vertices, we must start and end with one gap. Example of 4n plus 1 path is P9. If you plug in 2 for n, you get P9, and it's subgraph with C property here. You notice how the first one is a gap and the last one is a gap. So these patterns must be there for these paths to have a subgraph with C property. And also within these patterns, you can also notice the two edges followed by two gaps is consistently shown with both of these.
To summarize our research in finding patterns and paths in cycles for subgraphs with property C, we conclude that for all odd paths and all cycles with the amount of vertices divisible by 4, we will have a subgraph with property C. For a subgraph to have property C, it must never have 3 edges or 3 gaps in a row, and we generally want the edges and gaps to be in pairs because the end, besides the end of some paths.
Moving on to graphs with 6 edges. We wanted to find which connected 6-edge graphs have a subgraph with the property C. And in order to do this, we had to figure out how many there were to begin with. So we enumerated by hand all the possibilities, which we found to be 30 in total. Had we drawn out all the subgraphs, this would have been lengthy and possibly error prone. So this is why we decided to code to be more efficient.
All right. Okay, so how does our code work exactly? So we use Sage Math and CoCalc to classify the properties A, B, or C. It basically just takes a given graph and it proceeds to generate every single subgraph or all possible like subgraphs. Then afterwards, it checks for either properties A or B. And if one of the subgraphs appears to have neither of those properties, then it will come out as telling us that the host graph does contain a subgraph that has property C.
The results. We ran the 30 graphs into the code and found each graph's subgraphs and checked every subgraph for property C. We found 24 graphs that contained a subgraph with property C and 6 graphs that contain no subgraphs with property C. This means that there are 24 6-edge graphs that have maximal cohomological support and 6 that may not. These are the graphs that our code told us had no subgraphs with property C.
In conclusion, to find the maximal cohomological support, one way we solved this was to find all the graphs subgraphs with property C. So to achieve this, we created a code and checks if any graph subgraph has property A or B, using the patterns and rules for a graph to have property C. So in the future, this code can be used for larger graphs. For example, all graphs with 7 edges. Thank you.
Any questions? Yes.
Only if property C, is that a statement or is it a if full support then? Because you said that the 6 may not have full support, but
Right. So it doesn't like its associated graph doesn't have to have property C in order for it to have full cohomological support. It is only implied by property C. So property C implies it, but it's not like if it doesn't have property C, it doesn't have full cohomological support.
You go back to the graph.
Just go back to graphs.
Also, did you have fun?
Absolutely.
It was a lot of fun. We learned a lot. We learned a lot, but it was also fun to be with people that we know each other from a previous college prep program. So we're already friends. It was just fun to do it with friends.
Speaking for these three, or these two. Yeah, I mean, we did have fun. It kind of sounds demanding doing math for so long each day, but it works out in the end. Yeah, I mean, it works out in the end because, like Gabby said, we all know each other. It's all pretty fun when you know each other.
So personally, me and this guy right here, we are like gonna go to software engineer. So we both work on the code a lot together, and it's like I have a lot of fun doing that. And also it helps me practice for the upcoming school year.
So safe math is software.
So Sage Math it runs on Python. So I already know Python a little bit, so I just got to read like a documentation on like different functions that I can use for math specifically. So it's not it was difficult at first, but like once you get a hang of it, it's like really nice and straightforward. Yep. Yes. So I think approximately like 20-second, just go down. It just really optimized somehow. I don't know how we managed to pull it out, but it's just really nice.
You can say how
Hmm.
you can say how it only produces.
Huh? Can you repeat that? Favorite proofs, huh? Well, me personally, I didn't prove a lot of things, but I'd love to disprove my friends when they come up with something, right? So I try to find errors to just disprove them. It's fun that way, personally.
Me personally, I didn't have much fun with any proof because it was more you had to like be exact on everything, like very specific. In my head, I'm like, oh, I already knew this, but then you have to specify that because what if someone who doesn't know reads it and they're like, what are you talking about?
And then I disprove him. Get out. Just keep finding flaws.
Leave. Any more questions?
Yes.
So the theory connected graphs, what's our non-isomorphic?
Oh, yes.
How did you arrive at those theories? Sorry, can I look up the
Okay, yeah. So to arrive, well, we had a lot of trouble actually at first, when we weren't organized trying to find all 6 edge connected graphs. But then our lovely mentors over here, um, they showed us like methods to do it. So for cycles, we start with like the biggest cycle, and then kind of like if we have if it's a 6 edge graph, we obviously have like the full cycle. Then we have like a cycle with 5 edges and 5 vertices with like 1 edge kind of connected to it. And we went through all the possibilities like that for cycles. And yeah, for trees, it was also a very similar process. But we went from like the biggest cycle possible for 6 edges to like the smallest. And then, yeah, we just wrote them all out.
To be fair, I think it was pretty helpful visually, since if we were to like not put them on the board at all, we probably wouldn't be able to like understand them. Yeah. Any other questions?
Let me have a Okay, so one of the slides said that we only did 6 edge right now because the time limit that we had. But if we had like another week or two, we could use the same code to run for like any more graphics, more edges. So we can probably figure it out if
We would
any
have to
7 edges.
draw all the possibilities. So like we can just use the same 6 edge graphs we had, but then just try to apply one more edge and like see all the possible ways we can add one more edge to get the other 7 edge graphs. Any more questions?